I'll first start with a request. Yesterday in the panel, I mentioned some application of quantum information processors, and I should have mentioned application of foundations of quantum mechanics and testing theories like quantum mechanics. And in the last few years, I've been interested in testing Born's rule. And interestingly, I have challenge of finding theories which are kind of extension of quantum mechanics which violates Born rules. And I've learned from Scott that if Born's rule is not obeyed from a computer science point of view, everything goes to hell. But I would like to be able to compare different things in the experiment. So if somebody of you has a theory of quantum mechanics which is kind of violates Born rule or some extension of quantum mechanics, I'll be interested to have them. Okay, so let's go back to my talk this morning. I was supposed to give it yesterday on the session of using information to measure and manipulate, and when I was asked to talk about this, to me, as a physicist who works on quantum error correction, it was obvious that this was related in some form to quantum error correction, and I'm going to talk about this. And the challenge of giving a talk like this to an audience is, like this one here, is that there are some specialists who know quantum error correction incredibly well, and then they kind of look at this saying, okay, we know all of this, and there's other people who probably have never heard about quantum error correction. So I'll be putting two things together, some basic ideas of quantum error correction, and at the same time some recent results that my group has had. So hopefully I'll please both groups, and hopefully not displease both of them by kind of having the talk broken in two parts. So what is the goal of quantum error correction? Is to control quantum system using an amount of resources which is not too large. We want to do this because we're thinking about having quantum processor which use more and more quantum systems putting together, qubit as an example. And as we do this, the Hilbert space goes up exponentially. The goal of quantum information processing is to start with a state which describes a quantum system, evolve it to another state from which contains the answer to some question that you want to ask. And as you do this, evolving this, the Hilbert space is a matrix in, let's say if we use qubit 2 to the n by 2 to the n, goes up exponentially, and it becomes exponentially hard to get to the target of where we want to go. And one way of doing this is, instead of thinking about it through the Schrödinger equation, we can use what is called a quantum circuit, where we have time going this way, and then the quantum system in qubit and particle going this way, and these little things are what we call gates. And if the error per gate is 1 minus epsilon, and let's say they are the same for all the qubits, then the probability of success for n gates decrease exponentially. And means that the power of quantum computation to do something goes down exponentially if we cannot deal with errors. And the goal of quantum error correction is to take care of this. Now, the good news is that we know how to do this, and we've known how to do this for now about 10 to 12 years. And there's a theorem which is called accuracy threshold theorem, which says that a quantum computation can be as long as required with any desired accuracy using a reasonable amount of resource. And reasonable amount of resource, by what I mean here, is does not grow exponentially with the size of the computation that you want to do, the number of qubits that you want to do, or the resources that you have, as long as the noise level is below a threshold value. As if the error rate is too large, we don't know how to do this. Not that there isn't a method, we just don't know how to do this. So right now we just give up, don't do anything. You'll see that this threshold here is written in very pale letters, or kind of very pale, and this is on purpose. In fact, if I would be better at kind of PowerPoint or PDFs, I would make it fuzzy instead of pale, because we don't know exactly what is the value of this threshold, because it depends on a bunch of assumptions. I'm going to come back to this. If you have very good eyes, you'll see it's 10 minus 6, minus 5, minus 4, minus 3, minus 2, dot, dot, dot. And this is as a function of time what the threshold is, because by doing better construction, you get different values of this threshold, making different types of assumptions. I'll come back to this. But the important is there is such theorem, which tells us that at least we've done one piece of the work, is that we do know we can control quantum systems in a scalable way. And if you remember one thing about this presentation, this is the important one, and the rest is just fluff around this. So we know how to do this. I think the question which comes out of this, and if Bill Witter's around, and yesterday he says, what is quantum information really good for? What is this theorem really good for is that if we can turn it in practice and really control quantum systems. And we've had some start in there, but we're not there yet. So if you want the theorem, I think it's 10 to the minus 3, and there's some heuristics or some argument simulation which says 10 to the minus 1. But again, it depends on the assumption that you do. Okay, so here are some assumptions, and I think the most important one is parallel operation. If we don't do parallel operation between our quantum system, we don't know what to do, and we just give up. We need the ability to extract entropy, which is the same thing as measuring your quantum system, or sometimes you cannot do projective measurement. If you cannot do projective measurement, you have to extract this entropy or the noise. So error correction is like having a fridge. You have your quantum information in the middle. This error correcting codes is some kind of isolation around, and you try to extract the information before it corrupts the quantum information. You need to know what is the noise models, and it's easy to find noise models which will not be correctable. And there we pray that nature will be kind enough. Nature has been kind enough for classical computation to have similar types of theorems. So we hope that in quantum system the same thing will happen. And from the device that we have around, it seems that the noise model that we think of are kind of reasonable. So what are the ingredients of quantum error correction? So first, we have quantum error correcting codes, fault-tolerant procedures, and concatenation. And I'll talk a little bit about both of them. The three of them, one by one. So quantum error correcting code is a way of encoding information in such a way that it's protected against noise, and it's really what we call a triplet. We need to know what is the noise. We need to have a subspace which will contain the quantum information, so this is a part of the Hilbert space on which the noise model will act. And if we have these two parts, the goal is to find a recovery operator, an operator which reverses the effect of the noise. And we know that this happens when we have this equation where the ik's, ij's here are a basis for the subspace C. E are the operators which correspond to noise, and it's not too hard to understand what does this equation means, is that when j is not equal to k, we want the states which are orthogonal to each other to remain orthogonal with respect to the noise. If this doesn't happen, then you cannot kind of reverse the effect of the noise. The second thing that we need is when j is equal to k, we want the answer to be independent of what is the value of j over the value of k. So the zeros and the ones of our qubit have to shrink by the same amount. If they don't, then we'll lose the coherence. So this is what this equation is. So now I'm going to make one little diversion on this equation because I've learned that it's useful for something else, which is what is called quantum private channel, which is a way of encoding information, in fact, correcting for errors and encoding and protecting from an adversary who will look at you, have similarities with each other. And the idea of quantum private channel is the same thing as encoding to protect against eavesdroppers, but encoding quantum information instead of classical one. So you can find quantum private channel if you can find a set of operation, so for subspace psi, so that whatever psi that you have, you get the same state at the end. If you can do this, then people cannot trace back what psi is. So for example, for one qubit of information, you can find what the EAs would be, which is equal probability of having the unit operation, an X rotation, a Z phase flip, or a combination of both of them, which is the Y operator. If you have this equally, you'll get the rho 0 will be the unit operator. From the unit operator, you cannot know what you started with the states. So you can think about encoding as one instantiation of one of these operators. So you can be the person who wants to encode information, and your key is equivalent of saying, are you going to put 1, X, Y, or Z as the operation? If the adversary doesn't know what you're going to do, your quantum information, they cannot get the information back. So here's a little circuit which does this, applying the X, the Z operation combination of both of them. And why I bring this in is that now you have a different channel, which is called a conjugate of the one that you want to have here, which take the state here and send it to here, where we have two extra ancillas which apply this operation. And it turns out that the request to have a quantum operation which is a private channel is equivalent to having this dual channel and this subspace being error correcting of the equation we saw before. So there's a relationship between the two. Now for the people who know a lot about this stuff, the specialists in the audience, turns out that you can do something more general when the state is not pure. And this is something that has happened a few times in quantum error correction. If you want to know a little bit more about this, you can go and look about this private quantum channel. So I'm going to come back. So to quantum error correction, we have an equation which defines codes. And once we have codes, we can say, oh, we are protecting against corruption. Except that when you try to do this error correction, maybe you will induce more error than correct them. So how do you deal with this? And this whole idea here is called fault tolerance quantum computing. Okay. So what I want to do is to explain a little bit how does that work. So we can do this using a model of quantum computation where we think about this. So this is an abstract way of saying this is a quantum computer. We have an initial state we start with. We'll call it 0. And if you have many quantum systems together, it'll be the 0, 0, 0, 0, or any kind of fiducial state. We're going to measure in some specific basis. And then we have a set of gates. In the set of gates, we want it to be universal. And usually, if you look at your first introductory textbook of quantum computing, you'll have a generic 1-qubit gate and a generic and a specific 2-qubit gate. And with this, you can do any kind of quantum computation that you want. You can build any unitary transformation, measure anything. Now, this is great if you have no errors. If you have errors, you want to make these things fault tolerant. So I'm not going to talk of measurements and the states. It's relatively easier to do this, but the gates in the middle. There's a way to make gates here, for example, the 2-qubit gate here, fault tolerant using a concept which is called transversal gate. A transversal gate is one where the errors are propagating well. That is, one error doesn't lead to an exponential growth or many errors, which goes and create more and more errors. And this is what you're trying to avoid. So a little bit technical here. Let's say that we have a code which is 0, 0, 0, and 1, 1, 1. We're placing the logical 0, logical 1. We can make a gate which is transversal, which corresponds to the encoded flip gate, by doing a gate like this. This is good, okay? Because one error which will occur here will propagate to only 1 qubit, and you can use error correction to correct for that. The next gate here is a bad one, because if an error is coming here, it's going to propagate by doing the wrong control knot here, the wrong control knot there, wrong control knot there. And this will create one error, will create many of them. So this is bad. But fortunately, you can make it good by doing this construction instead of that one. So the whole idea here is to find circuits, find ways of manipulating the quantum information so that it's robust. So transversal have good error propagation properties. Now there's a theorem saying that there exists no quantum error correcting codes that exist a set of universal transversal gates. So people are not able to build a generic universal set which is transversal. So that leads to some trouble, that we cannot use that kind of idea. So people moved from there and said, can we do this robust? And it turns out the answer is yes. There's a construction which is possible, but it takes a lot of resources to make it happen. So people tried to simplifying it by using what is called a circuit with a restricted set of gates, which is form of a group, the Clifford group, the group which preserve the tensor product of Pauli matrices. So if you can do this, then you can show that there are codes where all these gates are transversal. Unfortunately, it's not universal. That this will give you only a set of gates which can be simulated efficiently classically. So you won't be able to do things which are real quantum computation with this. So you need to add one more thing. What people have suggested is adding one more type of state preparation. And it turns out that if you can prepare that state, this is a density matrix, and in the Bloch sphere is the one which is equidistant between x, y, and z. By adding this prepared state to this becomes universal, which is great. The next question is, what happens if this is not perfect? Well, it turns out that if it is not perfect, there's a way to purify it, to make it better, using only these types of gates. That's why it's called a magic state. Like there's something magic about it that kind of everything seems to fit well to make it happen. So I have 5 minutes to finish. So the difficulty of going through this is that it takes a lot of resources still to do this. In fact, there's a paper by Austin Fowler which shows that if you do a typical quantum computation, 90% of your effort will go into kind of purifying magic states. So is there a way of doing this more efficiently? And then for the next 2 minutes, this is a technical piece for the people who know the field. The answer is yes. So there's some work with Ben Reichert recently, some work with one of my students, Thomas Joachim O'Connor, which says if we take two codes, what is called a steam code, the Reed-Muller codes, you concatenate them together, you can have good propagation. Turns out that the steam code has these three sets of gates which are transversal, and the Reed-Muller code has this other set of gates which are transversal. But none of them has the full universal set. But you can make a construction which puts them all together. Turns out that both codes are what is called CSS, Calder-Bank-Shor steam codes, and they have globally transversal C0. So the C0 is transversal. The Pauli gates are transversal. Syndrome measurements is, for X and Z is transversal, and the error correction procedure is transversal. So what we are left with is the T gate, the one which create the magic state that we mentioned, and the other one is the Hadamard. So in 1 minute, for the people who know, here's the construction for the Hadamard gate. Each of this each element here corresponds to the steam code, and each of them have 15 qubits, which includes the Reed-Muller code in there. Turns out that the Hadamard gate is not universal for the Reed-Muller code, so error will propagate badly in here, but there'll be catch-up by the steam code. So we can make that code with an error propagation which is not that bad. And you can do a similar construction for the T gate. And so I'm going to just leave it as a show for people, again, the specialists in the audience who want to know this. But the importance of all this is that we might be able to reduce the amount of resources for quantum error correction. So I'm going to finish with this, is that we have a theory of quantum error correction. We know how to make error or quantum information robust against error impersonation of realistic devices. It takes an amount of resources which is not exponential, but still quite a lot more than what we need in the lab. So we heard yesterday that from Andrew Briggs that we need more algorithms, and I would say to him maybe in chicken tongue reply, what we need is not more algorithm right now, is more qubits. If we have more qubits, then we'll find some interesting thing to do. And the construction that I have on transversal gates is one which reduces the amount of resources that we need. We've been able to reduce the accuracy threshold, the value of the threshold. I think if we reduce the overhead that we have, I think we're on the way to build interesting small quantum processors. Error correction also allows us to think about different ways of manipulating information, and there are devices that would not work if you cannot do error correction. Example of this is linear optics quantum computing. Again, not much time to explain, but the upshot here is that there are ways where you can use error correction essentially in building devices. There are models of quantum computation, for example, adiabatic quantum computing, where we don't know how to do error correction, which raise question about are they scalable, can we make them useful? And that relates to one of question from somebody in the back last night of one of the challenges of certain implementation of quantum computing. And at the end, we need to have experimental implementation. So we are at the beginning of experimental quantum error correction. We have devices, we can show some small step of error correction. For example, they can encode information, show they can do a little better, but they only have one piece that goes into the accuracy threshold. We don't have fault-run gate, and I was going to mention concatenation. We don't have that yet, but it's in the way, and more qubit is needed to go into this. And then I have two little remarks on ideas of how to hide information, private quantum channel, where error correction codes are useful too, and some new construction. So with this, I will stop, and I'm probably within my 20 minutes. Thank you.